Now let's see the converse of basic proportionality theorem. The basic proportionality theorem with its own statement has proved that if a line is drawn parallel to one side of a triangle, then that line divides the other two sides in the same ratio. But what if I take it in the reverse way? Say for example, if I take the line which divides the other two sides in the same ratio, will that line be parallel to the third side? Is how we understand the reverse process of basic proportionality theorem, called the converse of basic proportionality theorem. So let's initially understand the statement and prove for the converse of BP theorem. So the statement in converse of BP theorem states that if a line divides two sides of a triangle in the same ratio, then that line must be parallel to the third side, is what is converse of basic proportionality theorem. So continue in the same ratio, then the line is parallel to the third side. Is how we understand the statement of converse of basic proportionality theorem. As this statement is compared with the basic proportionality theorem statement, we clearly understand that in case of basic proportionality theorem, given that a line is parallel to third side, we prove that the line divides the other two sides in the same ratio. But here, given that the line divides the two sides in the same ratio, I need to prove the parallelity of the line with the third side, the reverse process of understanding the BP theorem statement. Now in this case, the first thing is the given. So initially it is given that ABC is a triangle. Now in this case, I have D is a point on AB and E is a point on AC. Now, it is clearly given that the line divides the two sides in the same ratio. That is, if I join DE, then in that case I get a line DE such that AD by DB is AE by EC, is what is given with dividing in the same ratio. Now we had to prove, let's take the diagram of a triangle ABC where I have a point D on AB and point E on AC such that this line divides the other two sides in the same ratio. That is, AD by DB is equal to AE by AC is what we get. Now from this, let's see what we need to prove. I need to prove that the line is parallel to the third side. That is, my required to prove condition is that I have to prove this is parallel to the third side. That is, DE is parallel to BC is what I need to prove in case of the converse of basic proportionality theorem. So let's see the proof of the given statement using some mathematical properties. Cut. Now continue with the proof. Now in this case, the proof is by contradiction. Now proof by contradiction in the sense, because I need to prove that DE is parallel to BC, I assume that DE is not parallel to BC, then I come to a case where finally I prove that DE is parallel to BC. So in case of proof by contradiction, let me assume that DE is not parallel to BC. We go in assuming that it is not parallel. Let us assume that DE is not parallel to BC. That is, the line DE is not parallel to BC. Now, because this line is not parallel to BC, there must exist some line which must be parallel to BC. So, on our assumption that this is not parallel to this, let me take another line DE dash which is said to be parallel to BC, is how I assume for the given concept. Therefore, let DE dash be parallel to BC. So I assume this to be parallel to BC. Now, coming to the basic proportionality theorem, if this line is parallel to this, then this line divides the other two sides in the same ratio, is what we have seen in the Thales theorem or the basic proportionality theorem. Therefore, since DE dash, that is DE dash, is parallel to BC, that implies this divides in the same ratio. Therefore, I get AD by DB equals AE dash by E dash C. This is because by basic proportionality theorem, which has already been proved in the previous case. Therefore, this parallel to this implies this divides in the same ratio, is how we understand the concept. Now let me take this as equation 1. Now as I compare with the condition out in the given part, also it is given that the line divides two sides of a triangle in the same ratio. Therefore, AD by DB is AE by AC, already which we have obtained in the given statement. Given AD by DB is equal to AE by EC. Now, this equation 1 and equation 2, as I see, the left hand sides are equal, therefore the right hand sides must be equal. Now, as I see from 1 and 2, therefore from 1 and 2, AE by EC must be equal to AE dash by E dash C. By transitive property, I get this equal to this. Now, as I see here, AE by EC equal to AE dash by E dash C, let me add 1 on both sides of this equation. So when I add 1, I get AE by EC plus 1 equals AE dash by E dash C plus 1 is what I get when I add 1 on both sides. Now, by adding 1 on both sides, my intention is to take LCM in the next step to see what exactly we get. So when I take the LCM, this is nothing but AE plus EC by EC, which is equal to AE dash plus E dash C by E dash C, which I get on the right hand side by taking LCM on the left hand side and the right hand side. Now from this, if we proceed similarly further, I see that AE plus EC, which is clearly AC, because when I add AE with EC, I get the entire of AE plus EC is whole of AC. Therefore, in place of this, I can write as AC, and similarly, I can write this as also in terms of AE dash plus E dash C, which is AE dash plus E dash C is again AC, is what geometrically we get for the sum of each of the line segments. So let's substitute AE plus EC for entire AC, and similarly AE dash plus E dash C also as AC, and see what happens further. So adding 1 on both sides and taking LCM, I get the ratios in the following manner. So that when I have AE plus EC, I can just have directly this as AC. Therefore, AE plus AC, EC geometrically reduces to AC by EC. Similarly, when I take AE dash plus E dash C, also when added gives me entirely AC. So this gives AC by E dash C. Now since each of AC is common, I can cancel and I get EC equals E dash C. So what do you mean by EC equals E dash C? So as I see the triangle out here, I clearly understand that when EC is equal to E dash C, that implies both E and E dash are same. Only then it is possible that these two sides are equal. It's possible only when this and this converge. When the vertex E and the vertex E dash converge, only then EC will be equal to E dash C. Or in other words, if E dash lies on E, we say both EC and E dash C are equal. Therefore, in either of the possibilities, the next statement concludes that E must be E dash. Then what happens if E is E dash? We have assumed that DE dash is parallel to BC, therefore indirectly DE must be parallel to BC. Therefore, DE dash parallel to BC implies my E dash, which is equal to E, is finally where DE is parallel to BC, since E is equal to E dash. Since E is equal to E dash, therefore my DE is parallel to BC. Thus, concluding the converse of the basic proportionality theorem, which has been proved using the contradiction that DE is not parallel to BC, then assuming for one of E dash such that DE dash is parallel to BC, I use the basic proportionality theorem properties, which makes me again lead to E is nothing but E dash. Therefore, when a line is drawn in such a way that it cuts the two sides in the same ratio, AD by DB equals AE by EC, then also we get the proof that DE is parallel to BC as obtained here. This is what is about converse of basic proportionality theorem. So converse also holds true along with the basic proportionality theorem. Now that we have discussed about the basic proportionality theorem or the Thales theorem, let's see what is its application in real life or in general mathematics. So the theorem has its own significance in identifying the dividing of a line segment. The application of Thales theorem is that it helps us in dividing a line segment in the desired ratio. Say for example, I draw a line segment AB and I want to divide that exactly in the ratio 2:3 or 5:6, or I want to divide the line segment in the ratio 7:5. So I can divide any line segment in the desired ratio equally by using the Thales theorem. So let's see how we can divide a line segment into the desired ratio using the Thales theorem. So division of a line segment in the desired ratio. So first, initially, let me consider the line segment AB. So AB is the line segment which I want to divide in the ratio 3:2. Say for example, I want to divide this line segment in the ratio 3:2. So let's see how I can divide this line segment in the ratio 3:2. That is 3 parts and 2 parts separated on the line segment. So for this, initially what I'm going to do is I'm going to draw a ray in a suitable angle. let me draw a ray AX, making an angle with the line segment as some suitable angle. But this angle must be acute. This angle needs to be acute angle. So you can have any angle which, when we made using a protractor, you can make 30 degrees, 60 degrees, 45 degrees, etc., which are the standard angles, and then with the protractor you can draw the ray passing through that. But there's no specification that I need to use only one fixed angle, but this can be any acute angle which I can draw. So once I draw the acute angle, then I take a suitable measurement on with the compass, and then I try to just cut an arc out here. So initially I take some measurement and cut an arc out here, which I call it as A1. So from here, again, taking this as the center, I again cut an arc with equal measurement as AA1. So the length of AA1 is again taken with A1 as center, and then it is cut with an arc using a compass. Then I get this as A2. Then similarly, I repeat the same process by taking the same measurement as AA1 or A1, A2, because these two are same, and then taking A2 as the center, I cut an arc using the compass. Then I get A3. Similarly, I repeat the process to get A4 and then finally A5, because totally this leads to the 5 parts, 3 plus 2, which is 5. So in order that I have 3:2 as the ratio, I divide this into 5 parts. 1, 2, 3, 4, and 5 on the ray AX. So if the ratio varies accordingly, then this value is what defines on the number of times I need to cut to make it divided into equal parts, as with this figure. In this case being 5, because 3 plus 2 is 5. The ratio 3:2 is what I want on the line segment. So once I divide this into 5 parts, A1, A2, A3, A4, and A5 on the ray X, now next what I do is I join A5 with B. So next is joining A5 and B. Now clearly I identify that from this A5B is a triangle. So AA5B is a triangle which I'm going to utilize in dividing the line segment into the ratio 3:2. So initially for this, what I do is I try to take the third part, 1, 2, 3. So this is the point where the ray AX get divided in the ratio 3:2. Because if the line segment AA5, A3 divides AA5, or the line segment AA5, as which can be clearly seen as part of the ray AX, divides AA5 of the ray AX in the ratio 3:2, because A3 divides 3 parts here and 2 parts here. Therefore, A3 divides the line segment AA5 of the ray AX in the ratio 3:2. So the ratio is 3:2 on this line. Therefore, if I wanted to get the same ratio on the line segment AB, then I need to draw a line parallel to the third side, because my basic proportionality theorem says that if I recap with the triangle ABC, and then if a line DE is parallel to BC, then this line divides the other two sides in same ratio, that is AD by DB will be equal to AE by EC. Therefore, in order that this divides in the ratio 3:2, AA3 by A35 must be equal to some ratio on the line segment. And now the desired ratio is 3:2 on the line segment. Therefore, I can get the point on AB if I can draw a line parallel to A5B. So how do I draw a line parallel to A phi B, or this line, using the concept? Now BC is parallel to DE, so your BC here is A phi B, through which I have to draw a line parallel. In order to draw a line parallel to A phi B and passing through A3, we know that two lines are parallel if their corresponding angles are equal, or the corresponding angles are equal if the two lines are parallel. Now because these two corresponding angles are equal, this angle, whatever you measure for using the protractor, must be equal from here. So what I do is, I take the protractor, I measure the angle here, say it is theta, and the same angle I measure from here on from left, and whatever I get here is theta, will cut the line on the other side. Say this is P. So once I get the angle theta from A phi, then angle AA phi B, which is theta, will also be measured from A3 with the same angle, and that gives me this angle as AA3P is equal to AA phi B. So that when these two angles are equal, the line which I have obtained here, which is A3P, will be parallel to the third side. So this will be parallel to this when I draw a line making equal angle as theta. Therefore, in the ratio, next, let angle AA phi B, which I have taken as theta, let me assume this to be theta. That implies, using this, that implies, because AA phi B is theta, I also make an angle make equal angle. So in this case, AA phi B is theta, therefore that implies A3P is equal to theta, such that A3P is parallel to A phi B, since corresponding angles are equal. Therefore, when this is parallel to this, is because this and this are theta, such that both of them being equal make these two lines to be parallel. Now therefore A3P is parallel to A phi B. Therefore, from this basic proportionality theorem, I get that when a line is parallel to third side, that the other two sides are in same ratio. AD by DB is equal to AE by EC. Using basic proportionality theorem, AA3 by A3 phi is equal to AP by PB. Therefore, by basic proportionality theorem, I clearly have A3 by A phi B is equal to AP by PB from triangle A phi B. Now in this case, we already know that AA3 by A3 phi is 3:2, because this divides in the ratio 3:2. Therefore, this is nothing but 3:2 of AP by PB. That implies P divides AB in the ratio 3:2. That is, I can identify the point P which exactly divides the line segment AB in the ratio 3:2. So division of a line segment in this problem desired for 3:2 is possible using the Thales Theorem, which says that the corresponding sides are in same ratio. If the ratio changes, the number of parts which are going to divide on the ray AX changes, and respectively we proceed in the similar manner as we have done for this. To recap with, initially I draw a line segment AB, and then to divide that into the ratio m:n, I first draw a ray AX making an acute angle from the line segment AB using a protractor, and once I draw an acute angle, I get a ray AX. Then on the ray AX, I take suitable distances and cut each time with equal distances everywhere, so that I get different parts here. Now the number of parts I divide, it depends on the ratio which is added up with the value. If it is 5, I divide with 5 parts. If it is 7, I divide 7 parts. In this case, I divide 5 parts, A1, A2, A3 till A5. And once I divide into 5 parts, the last part is joined with the last point of the line segment AB, and then we get a triangle AA5B. Now comparing this with the triangle ABC, I observe that I need to have a line parallel to this so that that line divides the other two sides in same ratio. AD by DB is equal to AE by AC. Therefore, when I want to divide at the ratio 3:2, I identify that at A3, the ray AX divides into 3:2 ratio. Therefore, from this point, I want to identify the other point on the line segment AB such that this line is parallel to this, just like D is connected to E for the parallelity of BE with BC. I want to find A3 connected with the other point on AB or the other side so that this is parallel to this, which can be done by taking the corresponding angles which are always equal. So if this is theta, this will also be theta. Therefore, we know this angle theta, which can be measured using a protractor, and then the same angle is measured here with a protractor, and when I join the line and extend, that line cuts AB at P, which in turn gives me the understanding that A3P is clearly parallel to A5B. So this is the line identified to be parallel to this, so that these two angles are equal. Now when this is parallel to the third side, immediately by using the Thales Theorem, that line divides the other two sides in same ratio. Therefore, AA3 by A35 will be equal to AP by PB, such that I get this equals this by using the Thales Theorem. But I already know that AA3 by A35 divides in the 3 parts with 2 parts. Therefore, this by this will be 3 by 2, which comes as 3 by 2, which is AP by PB carried from the previous statement. This clearly makes me understand that when AP by PB is 3 by 2, that means P divides AB in the ratio 3:2. Therefore, when I want to divide a line segment in the ratio 3:2, was possible by identifying the point P from here, so that I can clearly get the point on AB, which divides AB in the ratio 3:2. So any ratio, the method is the same, but the concept changes with the values. But ultimately, the construction process and the steps are one and the same. Now, let's continue with criterion for similarity of triangles. So what is the criteria for similarity of triangles? As we recap with the definition of similarity of triangles, we have come with the property or the definition that two triangles are similar if their corresponding angles are equal and the corresponding sides are in same ratio. So sometimes we reduce it to the most minimized conditions, that if the corresponding angles are equal, then we say that the two triangles are similar. So we have the 3 types of criterion for similarity of triangles. Similarly, when we have the 3 angles equal, their corresponding sides are in same ratio. Similarly, when all sides are equal, also gives us the understanding that their corresponding angles are equal. So ultimately, the 3 criterion which we are going to consider here will finally lead to the 2 important factors for defining similarity of triangles. That is, the corresponding angles must be equal and the corresponding sides must be in same ratio, is what we conclude from the 3 different possibilities or the 3 criterion for similarity of triangles. So what are these 3 criterion is what we're going to discuss. The first criterion is AAA, and the second is SSS, and the third is SAS criterion. So these three criterion will define the similarity of triangles. So therefore, let's see how each of the criterion is defined. To start with, AAA criterion for similarity of triangles. So what does AAA criterion statement says is very important before we understand the proof of AAA criterion. So initially, AAA criterion says that if two triangles have equal angles, that is, their corresponding angles are equal, have equal angles, then the sides opposite to those equal angles, the correspondingly equal angles will be in same ratio. Then the sides opposite to those equal angles will in same ratio. And hence, because the corresponding angles equal implies the corresponding sides are in same ratio, and therefore the two triangles are similar. So we are proving the condition of the corresponding sides being equal indirectly when the two triangles have their corresponding angles equal is what we are going to prove in this statement. So if I have two triangles with equal angles, say for example, given two triangles, let me say ABC and